Hello, welcome to the RC Wallet Vacuum channel. So today's video is going to be the first in a series I'm going to be doing on building a small engine dyno for these fifth scales. This one's going to be geared, towards the big bore, higher horsepower engines, but we'll still work on smaller engines. And also can be used to run electric motors and test battery packs for torque curves and stuff like that. So I'm building this as a absorption style dyno versus like an inertia. The reason I want this way is because this allows you to not only do inertial spin up type to check the torque curve of the engine as it spools up, it also allows you to vary the engine load on it and continue to hold the load on it, so you can get the engine loaded up and go over and tune the carburetor or whatever else you want to do. Now the downside of that, of course, is you heat the oil up. I wasn't planning on putting an oil cooler on this, but I suppose if it's run a lot of times in a, like especially if you go to a drag race, it's a hot sunny day, you might need an oil cooler, but for now I'm sticking with it as is. So being an absorption style, it uses hydraulic fluid flow and pressures to load the engine down. Now you can also, with that style, you can read the torque a couple different ways. You can either read the fluid flows and the pressures, or you use a torque arm. I'm going to be using a torque arm in this situation. So one of the design criteria I wanted to place on this was I wanted to have it very portable, so you could take it to a drag race event or an off-road race event and do dyno tests right there on the spot. So to get there, I thought I was going to have a problem getting there, mostly because of the monitor needing AC voltage. But I was able to find a DC or a voltage or a monitor that will take DC voltage in, so I was able to keep it self-contained. I'll get more into that in a second. But to keep the weight down, I'm building it all out of aluminum tube, so it will make it pretty portable. And as far as the self-containment goes, all you really need to, when you take this thing, is basically either access to an AC outlet or like a 12-volt car battery or a garden tractor battery or something like that. All the voltages will all be contained. There will be no need for a transmitter or receiver. There'll be a microcontroller on there that's going to read a potentiometer that's mounted on the operator station, and that will control the servo with a 900, I think it's like 1500 microsecond pulse to run the throttle. So that'd be completely independent. You won't need any other battery packs, just whatever power source you can get to it. So I'm not going to really dive into the hydraulics and mechanical stuff today. I'm just going to give a quick overview. Where I am going to dig in a little more to the electronics and the GUI for it. I wanted to get that stuff done initially because I figured that was going to probably be the hardest part. So I wanted to get something settled in on that before I started buying parts to build the rest of it. So today we'll take a look at some of the electronics involved. So before we venture over to the electronics, this is a CAD model of what I'm going to be building. You can see the tank and the monitor all mounted on there, and the little shelf there's where the keyboard and mouse are going to mount. That'll be the operator station right there. So I'm going to be coming with some more videos soon, and I will cover the mechanical and the hydraulics and the fabrication. I do have some of the fabrication started already, but we'll be getting more into that in the future videos. So let's head to the electronics. So we're really on debated quite a bit about how I was going to do this, but I figured this would be a good opportunity to use one of the small board computers. So I decided to use a Rasberry Pi 4, which is this device right here. I'm not going to go too much into what those are about. There's a lot of information out there on the internet with these things, but I'll just cover what's relevant for this particular application. So these things, they run a little Broadcom chip in there. I think it's BCM 2711 quad-core Cortex. And I believe it's running at 1.8 gigahertz. I think this unit here has 4 gigabyte of RAM on it. And there's multiple ways you can communicate off of these things. Let me see if I can focus in on a little more on this. So there's multiple communication protocols off there. Obviously there's USB, got Wi-Fi, got Ethernet, got Bluetooth. And then what's important here is this connector right here. That's the 40-pin GPIO. That gives you access to multiple digital IOs. Now, the nice thing about these Raspberry Pis is you can run the Linux operating system on there. It has a lot of built-in features. It's got its own text editing and spreadsheet operation, and the spreadsheet's going to be relevant to this particular project. I'll get more on that in the future here. And the nice thing too is you don't have to pay. It's all open source. You don't have to pay them that albatross up there in the northwest of the United States a lot of money to use their spreadsheet operations. So coming up off the GPIO there's 3 other communication protocols. There's the I2C, the Inter-Integrated Circuit, SPI, which is Serial Peripheral Interface, and then also UART which is typical of the years ago, the old RS-232. It's a universal asynchronous receiver transmitter, I believe it's called. That's a non-clocked. The other two are clock communication protocols. I'm going to be using the I2C. It's a 2-wire. There's multiple frequencies you can transmit it. I'm going to stick to the default of 100 kilohertz, which is more than sufficiently fast. The downside of that setup is you have really limited run. I mean, I got like 5 or 6 inch wires there. That's really you don't really want to go too much past that. I think it's going to be put into a nice little control box, so the range is going to be real short, so there shouldn't be really issues with noise. So they do have a lot of good features, but there are a couple of problems. Coming out of that GPIO, that's a 3.3 volt compatible only, and sensors and microcontrollers tend to be 5 volts, so that gets dealt with. I'll cover here in a couple seconds. The other problem is no analog inputs, and this project's got 3 analog inputs I got to deal with. And then the other issue, since it is running Linux and it's not a real-time operating system version of Linux, there's enough overhead that you can't do precision timing. You can't rely on it for calculating RPMs, even though an engine running even 10,000 RPMs is still only about 167 hertz. It's not super high, but it still can be a problem. You've got a lot of other stuff going on in your program. And the other issue too is you can't do the precision timing for a servo. It just chatters. It just won't work right. So there's other ways of dealing with that kind of stuff, and that's what I got over here. 2 microcontrollers. This one here its sole job is to simulate a RPM pulse going into this particular unit here. Now these are 2 of the old classic Arduino Uno R3s. They work fine, but I'm going to probably be switching over to this 4809 version. It's an Atmel 4809 AVR. It's got a lot more memory and a lot more power in there, so I'll probably be switching to that. But I am still going to have a second microcontroller, and I'll get more into that in a second. Now I wanted to have it all in one microcontroller, but there's an issue with the library I'm using for the RPMs and the library I'm using for the servo. Also, they both clash with, they're trying to use the same timer hardware on the microcontroller. So that's why I'm going to probably have the second microcontroller. And this 4809 I think has more timer resources. Maybe it'll work like that, but I decided it's best to just keep the throttle completely independent. No connection to anything else except the potentiometer and the servo. That way you don't have a runaway type situation. It doesn't get tied. It doesn't get held up if the other microcontroller was to lock somehow. Now, as far as what's going into this GUI for data, as you all know that engine parameters are greatly affected by atmosphere. So I wanted to make sure I was getting atmospheric data in. So if you do a run on one day in certain atmospheric conditions, and you decide to go through and do some modifications, well, you don't get a chance to run it for a couple of days while you got different atmospheric conditions. Well, if you see any changes in the engine, you really don't know for sure whether it's the modification you did or it has something to do with the atmosphere. So I wanted to make sure I track the atmospheric data into this so you can go back later on and compare. Another feature that's going to be in there is I'm going to have 2 thermocouples. One's going to be, I'm setting up for exhaust gas temperature and cylinder head temperature. And once again, you can go through and you can monitor as you're tuning the carburetor while you're varying the load on this thing to see whether you're leaning it out by watching the cylinder head temperatures, amongst other things. And then to read the torque, I got this this unit set up, this load cell set up right now. This is not what I'm going to be having in the end product. It's going to be, I'm putting a much more rugged S style in there, and it's got shielded cable coming off. Being in a spark ignition system, there's a lot of EMI, so you got to be in a lot of sensitive electronics. So you got to take a lot of that stuff into consideration. So this is good. I'll be demoing this here in a couple seconds, and this does work, but I'm going to have a much more rugged version in there. So as far as all the specific electronics here, this device right here is the atmospheric sensor. It's a BME 680 from Bosch. It does the same chip does atmospheric, it does a barometric pressure, temperature, and humidity. It also could do volatile organics with gas and stuff like that. But I'm not going to put that in there. I just want the 3 atmospherics going in there, and that's going to be read through the I2C network too. Then RPMs are going to be coming off of, right now, like I said, I got this simulated coming off that micro. On the machine, there's going to be a magnet and a Hall effect sensor on a separate disc up on the drive shaft. I'll get more into that when we're dealing with the mechanical end of things. So as far as the torque goes, like I mentioned, this is the load cell, and it's being read over here by this device. It's an HX711 24-bit Sigma Delta A to D converter. It's converting the data or the voltage coming off the load cell, converting it to I think it's a 16-bit word that comes out and goes through a two-wire interface. It's similar to I2C, but it's proprietary. Now that gets fed right in the microcontroller. As far as the load cell goes, I mean, there's 4 strain gauges on there, all set in a balanced Wheatstone bridge. And anytime you distort it, their mount, it unbalances the bridge, and this HX711 will detect that and output. Let's see what's next here. And obviously the horsepower is calculated off the torque and the RPM. And right now, this little blue thing, this little potentiometer, this is basically faking out for the thermocouples. These are the chips that are going to go in to read the thermocouples. They're like analog devices. I forget what they're called. 8495 or something like that. But they're a real high precision instrumentation amplifier. There'll be 2 of them, and they're going to be fed into the analog ports on the microcontroller. These other 2 devices are just voltage supply. One's 3.3, one's 5. I'm going to have to put in at least 2 more supplies. There'll be one for the monitor, which is a 9 volt, and then there'll be a voltage in there for the servo, which is like a 7.4. I'll probably put in for that. I might just stick with 6, but probably 7.4. So back over here at the Raspberry Pi, I didn't forget to mention that the operating system sits on an SD card. But then you can save data. You can save data to the SD card if you want, but I generally just save that off to the USB drives. But like I mentioned too that these are 3.3 volts only. Micros are 5 volts. So this little device in here is actually just a level converter. You feed it 3.3 on one side, 5 on the other side, and it will convert back and forth. In theory, in this case, I don't necessarily need that because with the I2C network, the way it's set up, the slave, or the master, which is going to be the Raspberry Pi, sets the voltage. So it'll set the I2C voltage to the 3.3. The Arduinos will work with 3.3 without a problem. But just to be safe, I'm putting the level converter in there to avoid any mayhem. Because if you put 5 onto that, you fry the Pi, and it's not necessarily a good thing. These are pretty inexpensive computers, like maybe $70 or so. Well, they were before the memory prices went crazy. They've skyrocketed recently, but they're a pretty powerful little device, and you can run a desktop computer off that. You know, you're not going to do any 3D CAD modeling off it, but it certainly is more than capable as a standalone desktop computer, amongst many other things. So the final thing I'm going to cover is going to be the GUI. I got a fairly rudimentary GUI in here. Probably fancy it up a little bit. This thing will be adjusted here. Let's fire the thing up. So all you got to the atmospherics over here, and the thermocouples over here. You got your main displays here. Fire it up. Get a little RPM going in there. If I go over here on this other side and hit this other program, this is the second Arduino. We'll boost the frequency up a little bit. Should see a RPM change. Yeah, there we go. So this we'll put some load on this. Start seeing some numbers come up on the torque. I don't have a calibration factor put in on the software yet for this. This thing's reading probably double what it's actually reality is. I'm not going to bother with it. I put the actual one in there. But as you can see, I'll put a little bit of weight on this thing and balance it on there. And then if I go back over here and start changing the frequency around, should see some changes on the horsepower with that same torque in there. So right now, basically, I got a loop. The RP4 is going through and it's reading the atmospherics. Then it's reading and logging them. Then it's going through and reading the RPM, reading the torque, then calculating the horsepower, and then reading the two thermocouples, and then just looping back and forth through. And it's got to do a lot of conversions between the micros and this, and then as you finish the run, you can get. I got a menu. Some of the menus set up here. Hit data, you graph it, and then you can graph the. I just got some fake data in right now, but that would allow you to graph the horsepower, torque, RPM curve. And so some of the data when it goes into the RP4 has got to be converted to, it comes in as ASCII characters, but it's got to be converted to text for displaying, but it's also got to get converted to floating point to go into the matplotlib library to be graphed. And it also has to be done that to go in so it can be saved as a CSV file. Like I mentioned earlier, the spreadsheet comes into relevancy because I'm going to take and send the data to a spreadsheet file so you can go back in later on into LibreCalc, which is the spreadsheet program in Linux, to do whatever kind of graphing you want to do on the runs you just had. And this also allows you here, should pop up, yeah, it gives you the ability to save the curve right there. But that's a quick overview of what's coming up. And I'll be diving into the fabricating in the next video and some of the hydraulics. So if you are inclined to the electronics side and you have any questions regarding some of the more specifics on the electronics and the software, because it was definitely an interesting adventure getting this software developed. There was times I wished I could have been able to find information a lot easier than what I was able to. A lot of times it comes down to basically throwing shit against the wall and see what sticks to get the software problems. I had a lot of problems with the SM bus interface on this, which is a layer of the I2C. But anyhow, it's working now, and I do want to just change the GUI and fancy it up a little bit, but I'm going to get to that after I get the mechanical end of things working. So in the meantime, thanks for watching. Stay tuned, there's more coming.